Have you ever wondered how JavaScript handles mouse events, AJAX calls, etc. in the browser side or accessing file systems or HTTP module in the server side? This is where JavaScript Runtime comes into the picture. Hi, I am Rohan Roy and let's get to it. What is a runtime with respect to a programming language? A runtime serves as an execution environment for a programming language, encompassing essential components such as function storage, variable handling, and memory management with the help of essential data structures such as queues, heaps, and stacks. In case of JavaScript, the runtime is a program that extends the JavaScript engine, providing it with enhanced capabilities to interact with the external world. It goes beyond the core engine's functionalities, enabling seamless integration with the surrounding environment. Additionally, the JavaScript runtime provides us with a range of features and APIs that enable us to build a robust application using JavaScript. It's important to note that both browsers and JavaScript-based runtimes have their own distinct runtimes tailored to their specific requirements. Browsers on one hand employ runtimes to handle web page rendering or user interactions, while JavaScript frameworks utilizes runtimes that align with their particular need or developmental paradigms, such as creating a server using Node.js. Let's define the JavaScript runtime environment. It encompasses everything that we need for JavaScript to operate, which includes necessary tools and engine that executes JavaScript code. It operates in a single-threaded manner, which means that only one set of instructions will be executed at a given time. Within the runtime, you will find web APIs, which is not inherent to JavaScript itself but plays a very crucial role in handling asynchronous tasks within the browser environment. However, when it comes to Node.js, it utilizes V8 engine, which is originally from a browser, Google Chrome, and expands its functionality through global API instead of relying on web API. How to find out which runtime environment is executing our script? In browser environment, the condition to check this is if type of window is object, then it's a browser environment. If this condition is true, then it indicates that the code is currently running within the browser environment. In the case of Node.js, there are two conditions that need to be evaluated. Firstly, it is necessary to check if type of process is an object. Additionally, the type of require is a function. Only when these two conditions are true, then it confirms that the code is currently running within a Node.js environment. For service worker environment, the condition to verify this is to check whether the type of import scripts is a function or not. When this condition is satisfied, then it confirms that the code is currently running within a service worker environment. By checking these distinct conditions, we can identify and adapt our code according to the specific runtime environment in use. Let's discuss the JavaScript runtime in depth by taking a look at all the components that make up the runtime environment. These components are JavaScript Engine, Web APIs, Callback Queue, Microtask Queue, and Event Loop. In this video, we will focus more on the browser runtime environment and not the other ones. Let's start with the first component, that is the JavaScript Engine. The JavaScript engine is responsible for translating and executing our code. The JavaScript engine is made up of three components: the interpreter compiler pipeline, the call stack, and the memory heap. The interpreter compiler pipeline is responsible for translating our JS code into native executable code. The call stack or execution stack is a data structure that keeps track of the currently executing function and where to return to when the function execution completes. When a function is called, a new execution context is created and added to the top of the stack. And when a function completes, its execution context is removed from the call stack and control is returned to the function or script that called it. It is essential for managing the flow of the execution and ensuring the proper order of function calls in our JavaScript program. The memory heap is a region of memory where dynamic memory allocation occurs. It is the space where objects, variables, and data structures are stored during the runtime. The memory heap is responsible for managing memory allocation and deallocation for JavaScript objects and functions, ensuring efficient memory management and garbage collection. The next component is web APIs. Modern web browsers provides us with wide range of APIs that offer us various functionalities for JavaScript development. These APIs can be categorized as follows. Document manipulation. The DOM API enables us to modify HTML and CSS, allowing creation, modification, and removal of HTML elements dynamically. It also allows us to change the styles of the web pages. Graphics manipulation. The Canvas API and Web Graphics Library API provides us with the means to programmatically update pixel data within Canvas element, enabling the drawing and manipulation of the graphics. Fetching server data. The Fetch API provides us with a standardized interface to fetch resources from a server across a network. It utilizes generic definitions of request and response objects, making it easier to retrieve data. The web APIs encompasses features such as event listeners, timing functions, and AJAX calls. These functionalities are stored in web API's container and gets triggered when specific events occur. For example, when a request completes, a timer reaches its set time, or when a click event happens, then a corresponding callback function is added to the callback queue for execution. These APIs provides us with powerful capabilities, allowing us to interact with and manipulate various aspects of web pages and allows us to retrieve data asynchronously. In JavaScript, callback queue or task queue is a queue that holds tasks that are to be executed in the future. The tasks are blocks of code which are processed one by one in the order in which they were added to the queue. These are synchronous blocks of code which can add additional tasks to the queue while they are running. While the call stack keeps track of the currently executing function, the callback queue keeps track of the functions that will be executed in the future. It stores these tasks as function objects. The event loop continuously checks the callback queue and processes them one by one. Each iteration of an event loop is called a tick, which means taking a task from the queue and invoking its associated function. The event loop waits for the current task to finish executing and waits for the call stack to become empty before moving on to the next task, which means during the execution of a task, it has exclusive access to the call stack. Meanwhile, a task can add other tasks to the queue to be processed on subsequent iterations of the event loop. Overall, the callback queue and event loop work together in JavaScript to handle asynchronous tasks, ensuring they are executed in the proper order and without blocking other code from running. In JavaScript, there are different types of tasks that can be executed. Let us explore them. Set timeout and set interval. These functions allow us to schedule code execution after a specific delay or at regular intervals. The callbacks provided to these functions are queued as tasks. XML, HTTP request, and fetch API. These APIs can be used to make network requests. When a request is made, the callback associated with that request is queued as a task to be executed once a response is received or an error occurs. UI rendering. When changes are made to the user interface like updating the DOM or applying styles, the rendering process is queued as a task to be handled by the browser's rendering engine. Event handlers. When an event such as a click or a key press occurs, then a corresponding event handler is queued as a task to be executed in response to that event. Request animation frame. This method is used to schedule animations and visual updates. The callbacks provided to the request animation frames are queued as tasks to be executed before the next repaint of the browser. These are some of the things that JS considers as tasks and uses callback queue to order their execution. The Microtask queue is a special queue that holds microtasks. These are synchronous blocks of code in JavaScript. It was introduced in ES6 to handle promise resolution callbacks. Microtasks are quite similar to regular tasks in terms of being blocks of code which are run synchronously. They have exclusive access to the call stack while they are running. Similar to tasks, microtasks can add additional tasks on microtasks to be processed by subsequent iterations of the event loop. In JavaScript, there can be several different types of microtasks that can be executed. Let us explore them together. Promise callbacks. When a promise is resolved or rejected, the corresponding callbacks that are attached to it are scheduled as microtasks. These callbacks are processed using the Microtask Queue. Mutation observer callbacks. The mutation observers are used to track changes in the DOM or document object model. Now, when a mutation is detected, the associated callbacks are executed as microtasks. Queue microtask. The Queue microtask method was introduced in ECMAScript 2020. It allows us to schedule a callback as a microtask, ensuring that it is processed using the Microtask queue. Process.nextTick. In Node.js, process.nextTick allows callbacks to be scheduled as microtasks. These callbacks are executed after the current operation is completed, but before the event loop continues. Now, what's the difference between microtasks and tasks? The main difference between them lies where they are stored and when they are processed. The tasks are stored in the callback queue and the microtasks are stored in the Microtask queue. The tasks are processed in a loop and the rendering is performed in between the tasks. However, the entire Microtask queue is processed and emptied out after each task is executed but before the re-rendering takes place. This ensures that the microtasks have the opportunity to execute before the next re-rendering cycle occurs. In summary, the Microtask queue is a separate queue that holds microtasks, allowing them to be executed at appropriate times during the JavaScript execution process. The event loop is an algorithm that continuously processes tasks and microtasks in JavaScript. It ensures the orderly execution of the code by selecting a task or a microtask from the respective queue and putting it in the call stack for execution. Let's look at the event loop algorithm from the top level. It follows certain steps. When the script is loaded and run, then it is evaluated, which means that it is executed using call stack and memory heap. After this step is completed, then the event loop algorithm will check if there are any pending tasks or microtasks. If there are, then it will run all the microtasks that are pending in the Microtask queue. After this is done, it will refresh, repaint or re-render the UI if it is needed. After that, it will run one task from the task or callback queue. When this step is done, then it will run all the microtasks, then re-render the UI and then run one task again. And this process will continue until all the microtasks and tasks are completed and there is nothing pending. Then it will exit. This is the event loop. Now, there is a bit of a confusion here, especially if you go over the articles that are in this topic, which specifies that one task is executed, then all the microtasks are executed, then the re-rendering of the UI happens, and then step 1 again. Now, this is correct in a way. What we need to understand is that the first task that is executed is the evaluation of the entire script. So, it evaluates the script and then it processes the tasks and the microtasks. Now, let's expand it a bit and discuss the event loop algorithm in depth. When a web page is loaded in a browser, then its entire script is evaluated. During the execution of the code, it may add event listeners corresponding to click events or scrolling events or keyboard events. It may make API calls with their respective callbacks or add timers to run certain pieces of code at a later point in time. This is what the algorithm will check next. If there are any pending tasks or microtasks. If there is nothing pending, then it will exit. But if there are, then it will wait till the call stack is empty. Then it will check if there are any microtasks in the queue. If there are none, then it will move to the next step. But if there are, then it will dequeue them one by one and run them until all of them are executed. Then it will check if UI needs to be re-rendered. If so, it will do it. Otherwise, it will move to the next step. After this, it will check if there is any task in the callback queue. If there is none, then it will move to the next step. But if there is any, then it will dequeue one task from the queue and execute it. Now, there may be other tasks that are pending. It will be processed in the upcoming iterations of the event loop. Now, during the execution of the microtasks and the task, they may have added additional microtasks and tasks in their respective queue. So the check happens to see if anything is pending or not. If there is, then all the microtasks are executed, re-rendering of the UI happens, and then one task is executed, and so on in a continuous loop until everything is completed and nothing is pending. And after that, event loop will finally exit. If you are enjoying the video so far, smash that like button. You will feel better. Let's discuss a few examples to see how call stack, queues and event loop work together, and we will visualize them during execution. In this example, we are running a loop which then registers one task and one microtask per iteration. So once we enter into the loop, we are using set timeout to register callback function t as a task. And since we are not using any timeout, t will be pushed into the queue immediately. Next, we are using queue microtask to register callback function m as a microtask, which will then be pushed into the microtask queue. Now, after each iteration, one task and one microtask will be pushed into their respective queues. Once the loop is done, it will dequeue m one by one from the microtask queue and push it into the call stack for execution. Once all 5 microtasks are completed, then it will dequeue t one at a time from the queue and push it into the call stack and then execute it. Each iteration of the event loop will process t until all 5 of them are executed. Now let's just quickly run this and see the results. Now in this example, we are using set interval along with set timeout and queue microtask. We create a constant interval that is assigned with the value that is returned by set interval function. The set interval function accepts a callback function p along with 0 as interval and a parameter counter with a field count that is initialized to 0. Now, set interval will register p as a task and push it into the callback queue. Let's clarify one thing here. The set interval won't push p again until the previous callback p is finished executing. In the first iteration of the event loop, p is dequeued from the callback queue and pushed into the call stack for execution. Inside the function, there is a conditional statement that checks if the count property of the counter parameter is greater than or equal to 5. Since the condition is not met, the set timeout function is called, which registers the callback function t as a task and pushes it into the callback queue. The queue microtask function is also called with the callback function m, which registers it as a microtask in the microtask queue. Counter.count value is increased by 1 and iteration 1 is logged. Now, in the next iteration of the event loop, m is in the microtask queue, which is dequeued and pushed into the call stack, which logs microtask 1. After that, it is popped out of the stack. We also have t in the callback queue, which is dequeued and pushed into the call stack, which logs task 1. After that, it is popped out of the stack. Now, set interval pushes p again into the callback queue and the entire process repeats itself. But this time counter.count value is increased by 1. This happens 5 more times, after which counter.count greater than or equal to 5 condition is met and the clear interval function is called with variable interval to stop the set interval, and p is popped out of the stack and the event loop exits. Now let's just quickly run this and see what the results are. In this example, the code starts by creating a promise object using promise.resolve, which resolves it immediately. Then a for loop is run 5 times. Inside the loop, the promise variable is reassigned with the result of the previous promise's then method. So then method is called with the callback function p, and after every iteration p is attached to the promise object. Now notice, we are adding then callbacks to the same promise object, which means that the next callback function p won't be added to the microtask queue until the previous p is finished executing. After the first iteration of the loop, p is registered as a microtask and it is then enqueued to the microtask queue. When the entire loop is done, then the script execution is completed and the call stack is empty. So p is dequeued from the microtask queue and is pushed into the call stack. Inside p, we will first log promise.then1 in the console. After that, call set timeout function with no delay, which means it will register callback function t as a task and enqueue it in the callback queue. After that, we are calling queue microtask, which will register callback function m as a microtask and enqueue it in the microtask queue. Then P is popped out of the call stack. After that, next P is registered as a microtask and added to the microtask queue. In the next iteration of the event loop, M is dequeued from the microtask queue and is pushed into the call stack, which then logs microtask 1 in the console. Then M is popped out of the call stack. Then P is dequeued from the microtask queue and is pushed into the call stack. Since we ran the loop 5 times, this entire process happens 5 times, which means that promise.then with I and microtask with I is logged 5 more times alternatively, at the end of which all the microtasks are processed. Meanwhile, task T is added 5 times, one after the other, in the callback queue. In the next iteration of the event loop, T is dequeued from the callback queue and is pushed into the call stack, which then logs task 1 in the console and is then popped out of the stack. This happens 4 more times and is logged each and every time in the console. After this, the event loop exits. Now, let's just quickly run this and see the results. In this example, we are using a loop along with promise, set timeout and queue microtask. We are running the loop 5 times, in which new promise is called each time with a callback E. Now, to clarify, the promise constructor and the execution of the callback E is synchronous, which means on every iteration, new promise is called and it's pushed into the call stack, and within its execution, E is also called, so it's also pushed into the call stack. Inside E, promise 1 is logged to the console. After that, set timeout is called with callback function D and 100 into I milliseconds, which means the first iteration will be 100 milliseconds, then 200 milliseconds and so on. Inside callback D, which will be executed later, we call resolve, which will mark the promise as resolved and register any callback attached to the promise as a microtask and add it to the microtask queue. After promise, we call then with the callback function P. Anyway, this happens 4 more times, which means that the value of I is increased each time until it is greater than 5 and the loop stops. In the meantime, we have 5 promises pending, which will resolve at 100, 200, 300, 400 and 500 milliseconds, and we have promise 1 till promise 5 logged in the console. After 100 milliseconds, set timeout function registers callback function D as a task and enqueues it into the callback queue, which is then dequeued and pushed into the call stack. Inside function D, resolve is called, which will resolve that respective promise. So P is registered as a microtask and pushed into the microtask queue, and D is popped out of the call stack. In the next iteration of the event loop, P is dequeued from the microtask queue and pushed into the call stack. Inside P, we will call set timeout function with no delay, which will register callback function T as a task and enqueue it into the callback queue. After that, we are calling queue microtask, which will register callback function M as a microtask and enqueue it into the microtask queue. Then P is popped out of the call stack. In the next iteration of the event loop, M is dequeued from the microtask queue and pushed into the call stack, which logs microtask 1 in the console, and after that, M is popped out of the call stack. Then T is dequeued from the callback queue and is pushed into the call stack, which logs task 1 in the console and is then popped out of the call stack. After every 100 milliseconds, the process repeats, and this happens 5 times and everything is logged in the console, and then the event loop exits. Now, let's just quickly run this and see what the results are. To summarize, when we run our JavaScript code in an environment like a browser, it will be parsed, interpreted and compiled into a native executable code, which is then executed. It is executed using call stack and memory heap. The call stack is used to keep track of the order of function execution and its context respectively, and memory heap is used to store all the objects, arrays and functions. This is JavaScript Engine. The web APIs, however, provides us with additional functionalities such as adding event listeners, making external API calls, or APIs to manipulate the environment itself. Also, they are fine-tuned towards the JavaScript environment that we are using. Now, these APIs give us the capabilities to create tasks and microtasks. And to process them, we have Callback Queue, Microtask Queue, and Event Loop. Whenever new tasks are created, they are added to the Callback Queue. Whereas, whenever new microtasks are created, they are added to the Microtask Queue. This gives us the capability to run some parts of our code asynchronously. Event loop, or more specifically the event loop algorithm, allows the runtime to manage the callback queue, microtask queue, and the call stack. The event loop has its own intricacies as discussed, but what it boils down to is that it will evaluate our script, then run all the queued microtasks, then re-render the UI if it's a browser, then run a queued task, then run all the microtasks again, and so on in a loop. These are all the components that make up the JavaScript runtime. If you have enjoyed the video, consider subscribing to the channel and check out this video on JavaScript Engine where we have discussed its components in depth. Or if you are interested in core JavaScript related topics, you can check out this playlist. Thank you for your time. Have a nice day. Namaskar.